All right, good morning, everyone. Let's get started with today's class. So last time we started our repeated measures exercise and we got through the default model and then two other models, including the compound symmetry, which is the simplest one, and the general, which is one of the most complex ones. So I went ahead already and launched my 06_RM project. Please go ahead and do that as well. Make sure you are in the right project. Then if you're not seeing yet your script here, make sure to open the script, the partial script we've been working with. And again, ideally, if you closed your RStudio project since last time and you reopen now, ideally you would not have any variables in any objects in your environment, because that's a setting that we changed at the beginning of the course, and I recommend you doing that for any projects so you don't create ghosts of your objects in between different runs. So as it is my case here, I don't have any of my objects. What I want to do is, so we did a lot of things already, but I'm going to come here. We stopped. So if you look on the outline, we stopped at model 3 general comparison. So this chunk here was the last one that we ran. However, for us to reproduce this and everything that we already did, you can go to the next chunk, which would be the one running the model for model 4, AR1. If you come to this chunk here and you click on this button, it will run all chunks above, and that will create all the variables that we have already created before, which we will need to continue. So make sure you do that. And I actually got an error. So when I check class 1, let's see. So I actually had an error, or had a I had a chunk that had a piece of code that did not work. Maybe I left some code that that I wrote something above on an object that did not exist yet. Okay, right here. So my class mod1, I guess we don't have a mod1 anymore. So I'm just going to delete that. Well, now that I think about it, if you run all above and it goes through those chunks where you have the intervals, if your intervals gives you an error, which I guess for some of you it was given, and it was given to me in different cases, maybe the run all above is not going to work because it's going to stop there. So maybe let's just, yeah, let me restart here. So let's just go from the beginning and run the chunks that we have to run one by one, so we know we have them. So load the packages, read in the data, and we also did some light wrangling there. So run this chunk. We can skip the summary. So any chunks that we're not creating objects, you can skip, because those were just for visualization at those points. So here we have to go ahead and run this whole chunk here for the, well, yeah, I mean, we can go ahead and run it all. We are not using the mod1 default LMER afterwards, as we talked about. But we are setting here the correct contrast to sum to 0. So we have to have that part run. And then on the next chunk, you do want to run the mod1 default. That's going to be our baseline for comparison purposes. Make sure you have that run and have that object on your environment. You can skip ANOVA. We're not creating any objects there. You can skip ACF. Make sure you run mod2 CS as well, as that was one of the models we ran. Again, you can skip ACF, you can skip intervals. You can skip the ANOVA. And then you get to model 3 general, run that. We want to have mod 3 gen object in our environment. You can skip ACF, can skip intervals, and can skip the last ANOVA comparison. I guess maybe we can just follow up here again on this, because since was the last thing we talked about last class, let's just run this and again take a look at here. So what we're doing here is we have the default model that is assuming a correlation of 0. So it's not even trying to estimate, it's just setting that correlation to be equal to 0 in that error matrix. That's our default model. Then we have the compound symmetry, which is allowing, it's just calculating one correlation coefficient for those 4 days. So it's the simplest one, only takes one extra degree of freedom because it's just one more parameter that it is estimating. And then we have the general, which is the most flexible one that calculates actually one correlation coefficient for each pair of different dates within our repeated measure. That's why it's taking 46 degrees of freedom out of this model. Then we did the comparison using a KK information criterion and also Bayesian information criterion, AIC and BIC. And we noticed that in this specific case, if we use AIC as our metric to select the best model, we would select Mod3 Gen because it had a lowest AIC, at least within these three models, right? We're still going to test other models, but within these three, Mod3 Gen had, so the general correlation structure had the lowest AIC. However, if we look at the BIC column, that actually had the highest BIC, so the worst fit. So in this case here, the two metrics we're using did not agree on which one was the best model. And we're just gonna keep that in mind as we move forward. All right, so that was the quick recap of what we did last class. Now let's go ahead and keep going with our exercise and fitting other correlation structures. So now we're gonna run here the autoregressive order 1, AR1. So if you remember from the lecture, this model here basically is going to, it is autoregressive level of order 1 because looking at one time lag and relating that immediate previous time lag with the current one and taking that, that correlation into account. So I left you here the LME function already, just as a reminder. With LME, the formula, so we have our response variable yield explained by the fixed effects. Just as a refresher, we're having the days after planting as a factor being part of our fixed effects because, again, now we're interested in that time effect. And then on our random is a little bit differently specified than LMER. So in LME, it has its own argument where we specify the random effects. So this was a randomized complete block design with a split plot. That's why we have the block being the largest level. And then we have potassium rate nested in block. That's what sets it as a randomized complete block design as a split plot. Now, because we do have different dates of harvest, that creates another level of hierarchy in this model. And remember that the last smallest level of hierarchy, we do not specify in the random effects because that goes into the residual. However, because we do have that before we had repeated measures, N rate was our smallest level of hierarchy. So we were not specifying N rate in the random effects before this exercise. Now N rate is not anymore the smallest unit of hierarchy in this design. It is actually date. So that's why we have to include N rate in this random effect. So only the date effect goes into the residual, and that's what we're testing. All right, so here on LME, if you remember, there is an argument called correlation. That's what I want you to do next. So here's where we're going to specify the correlation structure function, which in this case, for an autoregressive of order 1, is going to be core. In this case, is going to be core AR1. And just to remind you, in this case here, core AR1 and core CAR1 would be equivalent. The CAR1 is for continuous autoregressive, and it's a case, it is the only of the temporal correlation structures that we're using, it is the only one that would accommodate different intervals between dates, right? In our case, we have the same interval. We have 120, 130, 140, 150, so 10-day interval between all dates. So in our case, it would not matter. However, if in your case you have different interval of dates, so let's say you have 0, 5, 7, 10, right? So an interval of 5, of 2, and of 3. So at different intervals, the core R1 would not work. You would have to use the core CAR1, which is the continuous autoregressive, which allows you to have different time intervals between your repeated measure. So in our case, we're going to use core R1. And really, we're just going to use that argument here that is called form to say that it is over DAP. If you remember our data set here, RMRCBDTF, it has the factor days after planting, which we forced to be factor, and we also have the numerical days after planting. The reason why we're using the fixed effect up here, or I'm sorry, not the fixed effect, while we're using the factor up here on the fixed effect and the numerical on the correlation is because we want the means of each one of those days. If we want the mean, it has to be a factor. If we leave here as days after planting as numerical, it's going to give you an intercept and slope. So it's not going to give means, it's going to do a regression. And then we give here as numerical on the correlation because it needs that to understand what's the interval difference between the time dates. If we give on the correlation the factor, then it's just, even though it's going to be a factor and it's going to have levels 120, 130, 140, 150, but because it is a factor, it might as well just be called A, B, C, D, right? Because it's a factor. And so it's a categorical variable. So if you give a categorical variable here, it's not going to be able to calculate the interval between them. So that's why we do a factor days after planting on the fixed effects because we want the means, and on the correlation we give as numerical so we can calculate the interval between them. All right, so don't forget to add the comma after here so your code runs well. So let's go ahead and run that and inspect the output. So very similar output as far as giving us the coefficients of the fixed effects first. And then it's going to give us the random effect summary. So the standard deviation of different levels of our random effects. And then it's going to give us here this argument called phi1, which is the correlation being calculated from this type of structure. And we see here that the value that is estimated, at least on my side, is 0. I think it's probably 0 on your side as well. So this is just, telling us that the correlation is 0 here, that was estimated. So in this case, as we've seen with previous models as well, if the models that were able to calculate the correlation coefficients, that was very small. And some of them, the intervals were including 0, and others were not even able to calculate intervals because that value was so small. So again, here checking on a different correlation structure, we're seeing a very small, or in this case, a 0 estimated correlation. All right, so let's inspect the autocorrelation plot. I left you the code, so you can just go ahead and run it. It's interesting though, because so if you stay here, stay on this chunk. Well, actually, let me do this. Let me pop this out so I can show you something else for comparison purposes. So I'm going to come back to the model 1 where we had the ACF for that model. So if you notice now, it's actually very similar, right? I would say it's probably right on top of it because it estimated the correlation to be 0, which is what the model default is doing anyways. It's just that the default is assuming to be 0, is not even trying to calculate. And in this case, all the other ones are calculating some type of correlation. So in this case, the autocorrelation plotted different lags here from the AR1 correlation structure. That is actually looking pretty close to the model 1 default, which again, probably because the AR1 estimated to be 0, and that's what the default one assumes by default. So let me come back to where we were right here. All right, so we see again that these correlations at lag 1 and 2 are significant, not at lag 3, but that correlation is being estimated at 0. So that is an interesting point there. If we check the intervals, on my side, it does not estimate because I think it was 0. I think that's what's going on. But let me check this. Did anyone get a different output? Was it able to estimate for anyone? Okay. That's what I would expect. And I think it comes back to the fact that that correlation that was estimated was equal to 0. So it has, it has a hard time giving us intervals for that. All right, that doesn't keep us from comparing this model with others. So I left you the code here already. The only difference here, so we're going to be doing this, right? And we're going to keep the models that we have already developed and then add the one that we're working on right now incrementally to compare all of them. So if you run that, we see here that actually it's taking one more degree of freedom than our default to estimate that correlation parameter, but it has and because of that, so it took 1 degree of freedom to estimate something that was estimated as 0. So this is a case where it is taking degrees of freedom, but it's not helping the model to improve fit. So we see AIC go up. Similarly, we see that with BIC as well, compared to the default model, right? So it's taking up information and not giving you back enough to cover for that. So we see an increase on AIC and BIC, which is interpreted as a more poor or poorer, I guess, model fit in this case. All right, so let's go, let's fit on the next model here. So the next model is going to be the autoregressive moving average. So the book calls this ARMA. I've seen this being called ARIMA. Is a very popular option for repeated measures as well that we're going to be using here. Again, I left you most of the formula there. The only difference is we're going to add that correlation argument. So if you come here and you say correlation equals to, we want to use the core ARMA function. And here it takes 2 arguments. So one is P. So P is the order of the autoregressive part of that, which at least I want to propose that we do a ARMA 1-1 model, which would be the P. So the number of legs of the autoregressive order part of it is 1. So it's looking back into one time to do the correlation with the current time. And then it has a second argument that is Q, and Q is the order of the moving average. So the moving average, again, it's similar to the autoregressive, but it does that on the residuals instead of the actual values. And it is also the number of time points you go back. So to do a ARIMA or ARMA of order 1 on the P and the Q, that's how we would specify. And I'm just going to show you this model, but just to keep in mind that both for the AR1 model and the ARMA 11 model, these models here, so in our case, we only have 4 time points, so we don't have a lot of room to play with how many data points back in time you want to include. But let's say you have a time series with 50 points or whatever, right? I mean, a lot more points than we do. You can really play around with these numbers and say, I want to calculate the correlation of the current time point and correlate that with going back in time to 2 levels, let's say, or 2 dates or 2 depths. So that's what you would change here on the P and the Q. So we're just going to be doing the 1-1, but you have flexibility there if you have reason to believe that, including more lags in that correlation calculation would help your model. All right. Don't forget to add the comma and let's run it. Now, if we print that to inspect what the model did, again, it has all the fixed effects, has the random effects, and then it has this correlation structure here that now has 2 estimates, right? So it has an estimate of phi, that's for the autoregressive part of it, and it has an estimate of theta, which is the estimate of correlation for the moving average part of the model. And here we see that it was able to estimate the correlation, and phi was negative, theta was positive. All right, let's take a look at the autocorrelation plot. To tell the truth, is really similar to the AR1 and the default. And it may be because the correlation overall is weak on this specific data set. But we see that it did not help us to fix the correlation here being beyond the dashed lines. If we get the intervals, at least on my side, it runs. And then we see here, we look at the correlation structure and on the intervals of that. So we see that in both cases, so we have an estimate, right? That's the same that it was coming from just when we just print the model. But now the lower interval in both cases. So what we want is, the way that we interpret this is if your lower boundary is negative and your upper boundary is positive, it means that your interval includes 0. And if that's the case, then we say that is not significantly statistically different from 0. So there was something that was estimated, but it was not significantly different from 0. And we see that here with both phi and theta, right? So we see theta as well having a lower on the negative side and having an upper on the positive side. Just for us to think about it, just because you have a negative, I guess, upper or lower, that is not what makes this being non-significantly different than 0, right? Because let's say if your correlation is negative, but both your lower and upper are on the negative side of things, then it is significantly different from 0, but it's negative, right? And similarly, if both of the lower and upper would be on the positive side, then it would not include 0. So you would be significantly different from 0 on the positive side of the correlation. All right, so let's go to the next chunk and look at the ANOVA and compare this model. So this model here actually had a worse fit than the previous ones, is at least looking at AAC, right? So now it compared to the default, it's taking 2 extra degrees of freedom, 1 for phi, 1 for theta. And because those correlations are so small, it's using these degrees of freedom and taking it out from the error, but it's not providing a better fit. And therefore it makes our AAC models, our AAC values increase, indicating a worse fit. All right, so up until here, so from model 2 through 5, these were all serial correlation structures. Serial correlation structures, they work for temporal data because you have one directional potential correlation, right? So time only moves one direction. Now we're going to get into the spatial correlation structures, which are most commonly used for spatial data. So because you have 2 dimensions now, you can change X, you can change Y. In our case, so the spatial ones are used a lot in precision ag, because let's say if you go to a field and collect a sample and you have a GPS coordinate of it, you're going to have the X and Y coordinates. In our case here, we are not working with spatial data. We're working with temporal data. However, these functions that are made for spatial correlation structures also work with temporal data. So that's what we're going to be using, and that's why we're going to be using them. And another benefit of them is that they do, so regardless if it's temporal or spatial, all the spatial correlation structures will accept intervals that don't have to be the same, right? So if you imagine you go to a field and take a whole bunch of coordinates, you'll never really, like, you don't have to think that I'm going to take exactly like 1 meter here and then 1 meter away and so on. Like, you just take wherever you take it, and the model allows for that difference in intervals. In this case, in space, or in that example, in space, right? In our case, we're still on the temporal, on the time side of things. And in our case, the intervals are equal, but if they were not, then we would also be able to use all the spatial correlation structures. All right, so again, I left you the model already. The only thing we're changing is that correlation. So we're going to come here, and on that correlation argument, we're going to use core EXP. Or in this case, exponential is going to be our first model. And really the only thing we're changing as well is saying that the form equals to tilde DAP. So it knows how to calculate those intervals, or the intervals between the time points. Okay, so if we run this and we print this, we get a very similar output as far as fixed effects. We get our random effects, and then we have our correlation structure. So here is saying exponential spatial correlation, and it gives us an estimate of range. So this is a different concept now from the temporal or serial correlation structures that I do want to bring your attention to this, because there's going to be a few differences on how we evaluate this model. Before we do that, I do want to show you again the lecture, because I think now it may be easier for us to visualize what this range means if we go back and look at the slides. Okay, right here. So this is what these spatial models are doing. So this was not done by the temporal models. This is what is happening with the spatial correlation structure models. In this case here, so we have the rational quadratic is one type of spatial correlation structure. We have spherical, exponential, which is the one we're doing right now, Gaussian, and linear. So what happens here is we have the distance, so these numbers are not matching ours, but this would be probably a distance in meters, let's say. And then we have the semi-variogram. So what the semi-variogram does is it takes all points that in this case, let's say, have a distance of 0.5 meters from each other, and do the correlation of all those points. And then increases the distance of the radius, you can kind of think about in a radius perhaps, and it goes to the next level. So now all the points that are spaced by 1 meter takes the correlation of that. And then all points that are spaced by 2 meters and does that correlation. And that's what we're seeing here on the semi-variogram. The difference, though, is that this semi-variogram is not correlation. It's actually the opposite of that. If we were to plot here correlation would be kind of like mirroring on the flip side of what we see at the semi-variogram. So correlation would be very high for lower points, and it would decrease. So correlation and semi-variogram go in opposite directions. So we can kind of think about here that points that have very low semi-variogram are the ones that have very high correlation. What we're trying to do here is to give an estimate of the range. What is the range? So the range would be, we fit all these different models to our data, and we try to find the range, which is the point after which the semi-variogram plateaus out, which also means that your correlation plateaus out. So again, coming from the spatial context of thinking about if you have like a field where you take a whole bunch of soil samples that are georeferenced, and we want to know what is the range of, let's say, soil phosphorus in this field. So in this case here, the range of all of these models is 1, which is where all of them kind of plateau out if you go to the x-axis. So that would say that points that are away from each other up to 1 meter, in this case, I'm assuming this is meter, are correlated, and we should account for that. But points that are farther away than 1, in this case, 1 is the range, are not correlated. So we can assume a correlation of 0. So what these models are doing behind the scenes is calculating the range. So they're trying to estimate where is that breakpoint that of distances, or in our case, time intervals that are lower than the range. You should estimate a correlation, which the model does for you. And after that point, you don't have to estimate that because it's 0. And again, range is the point where these models plateau out, right? Is that distance on the x-axis after which they plateau out and the y-axis. Let's see, another thing I wanted to tell you about this. Yeah, so even though in these plots here, we're just seeing the lines, we're not seeing any points, but these lines are the models that we're trying to fit to the semi-variogram of our data. The reason why we try multiple different types of models is because maybe one of them is going to give a best fit to our data. And then that's probably the one that's going to have the lowest AAC, and that's the one that we keep using for inference afterwards. That's why we fit different ones, and not just one of these, and say, I check for a spatial, I check one model. Wait a second. You should check more than one, because maybe a different model is going to be a better fit to your data. So again, we're doing the exponential that is going to try to fit this line to our own data semi-variogram. Let's see how that looks like. All right, so we can still use the ACF, the autocorrelation function here. It's still very similar to the default, which tells me that it's probably not doing a great job. And now I want to introduce you this new function here. That's the variogram function that we're first, if you just run the variogram on mod6 exponential by itself, it gives you a table with the distances, the number of pairs you have for each one of those distances. In our case, the distances are the time intervals, right? So we have here distance of 10, 20, and 30 because our time intervals are 120, 130, 140, 150. If you take the distance between them is 10, 10, 10. So 10, 20, and 30, the cumulative distance difference between our time intervals. So that's what's here. You see that the number of pairs is changing, and that happens always because within a given, with the smallest distance that you're considering for this model, that's where you're going to have most data points being at that difference. You can kind of imagine a map with a whole bunch of points. Imagine the number of pairs that are 1 meter away from each other. It's probably many. Now imagine the number of pairs that are 50 meters away from each other. It's going to be less points that are going to have that common larger distance than the ones that are closer. So that's why a number of pairs here decrease as our distance increases. And then once we plug that into the plot function, it just makes this plot for us, which is exactly the same plot that we were seeing on our slides, except for a couple of things. So we have semi-variogram on the y-axis. We have distance on the x-axis. Notice how now this distance is in terms of our difference in interval of the timestamps, right? So again, we had 120, 130, 140, 150 days after planting. If you take the difference of that, it becomes 10, 20, and 30, which is plotting here for us. So it's calculating all the correlation for time points that were 10 days apart, and then 20 days apart, and then 30 days apart. And those are our actual data points. Now, the reason why we don't have a line here is because it was not able to fit an exponential model to these 3 points, which I guess you can kind of visualize that because our points are here, here, and there. And the model was trying to do this, right? So it's not going to fit points that are like this. So that's why we don't see a line because it was not a good fit. And in our case, again, we have only 4 time points, which translate into 3 distances to be calculated in the semi-variogram. That is really not a lot of data points, right? To fit any curve really of this, in this case, the exponential. So in your case, if you have more time points or if you have geospatial data that you're probably going to have a lot of points, which is going to give you a lot of distances here, you would be able to fit that. All right, so if we check the intervals, let's see, for me, it runs, and we check the correlation structure. So it's going to give, again, what is calculating as the correlation is the range, is the value, is the distance after which the correlation plateaus out. For us, it does not include 0, but it's very wide and is even weird because we don't even have a value of 29. Or no, sorry, we do have 30. Yeah, we do have a distance of 30. So I guess I was getting ahead of myself. So it does comprise the intervals that we do have, but it's very wide, right? So he's saying that correlation would plateau out somewhere between 0.4 days and 29 days, which is basically the whole range of our data. So it's really not useful. It does not, however, it does not include 0. So it is significant, but highly variable. All right, if we come to the ANOVA and compare. So we see that the exponential compared to all the previous, compared to ARMA and AR1, it had a better fit than they did, but it was not the best fit yet, right? So the best fit still remains the general, which was the most complex one. All right, so we're gonna just keep going down the line here, where now for all the spatial ones, really what we're doing is changing the model that we're trying to fit to our data, right? To our residuals, which is these different ones. So now we're gonna use the Gaussian, which is gonna try to fit this curve to our data and see how that goes. All right, so to do that, again, we come on the correlation argument. and this is gonna be called core Gauss is the name of the function. And we just, the same way, we just say form equals to tilde DAP. You can go ahead and run that. Now, the output's going to be very similar because it's still going to give us a range. So all of these spatial correlation structure models are estimating the range, and that's what they're giving us, which was not the case for the serial ones. The serial ones, some were giving us what they would call phi or theta or rho. They're calculating different terms and different named terms as our correlation. All the spatial ones are giving us a range. So here, the estimate of the range is actually 6 days. So it's saying basically that up until 6 days, the data points are correlated. After that, no correlation in the data. Let's look at the autocorrelation plot again. Still very similar. Lags 1 and 2 are still going beyond the limits that we have here, so that's not what we want. Let's look again at the variogram. Still, we don't see a fit, right? We see our 3 points, we don't see a fit. Again, because this data here only has, four time points. So we're having that issue of actually getting a fit of these points. If you check the intervals, we see that it still gives us, so our range is ranging from 2.4 to almost 16 days, with the estimate point being at 6. So it's still wide, maybe a little bit less or a little bit narrower than the previous range when we use the exponential model, but still quite wide. And it's different from 0, right? So that does not include 0 in the interval. So it is significant, but it's still very variable. Now, if we check the ANOVA model again, we get a very similar EAC of like 13, 36, just a little bit different on the decimal points. So again, it's not our best model, right? Our best model remains the general model, at least if we are using EIC to make that decision. All right, let's go to our next one. So this is the linear. Is the linear spatial? So just to not get you confused, I want to show you here. This is what the linear is basically a broken line model. That's what we're trying to fit. So correlation equals to core lin is the function. And again, we say form equals to tilde DAP and give it a comma. We run that, we can inspect it again, go all the way to the end of this summary. We're gonna find also a range. Now it's telling us the range is almost 11 days. So we're getting different estimates of the range for these different spatial models. If we look at the ACF, still looks very similar to the previous ones. So it's not really improving when we look at this plot. And then let's look at the variogram. Same thing. So it's not showing us that line because it's hard to fit these 3 points within those shapes that the functions are applying. Let's check the interval to see the interval of the range. So now it's a little bit narrower still. So a range starting at 10 and going to 24. So it's becoming a little bit more precise, I guess, but still quite variable here, especially because our data only has, it goes from 0 to 30. So it's almost covering the whole space. Then checking on the ANOVA, it is actually exactly like the Gaussian, right? So we're seeing that. And again, this is happening. And I hope that I guess I hope a couple of things. The first one is that you notice that overall, even though this is repeated measure data, there's not a lot of evidence for actually correlation of the errors. And this it could happen, right? Just because it is repeated measure, it doesn't mean that it will be correlated. That is our hypothesis coming in, because we know we did not randomize, but then we have to check it to see if that's actually true. And in this case here, we're seeing the models not being very different from each other because of that. And I hope you don't get discouraged, I guess, from the fact that we don't have a lot of our correlation here, because really the goal is for you to understand what you would do on your side when you have repeated measures. You would follow the same exercise. I guess regardless if you do have correlation or not, but at least the process is going to be the same regardless of that outcome. All right, so after checking this model here, we're still coming to the conclusion that the general is the best if we use AAC as our metric. And then the next one here, or the next, and I think the last, no, we have two more. So the next one is the rational quadratic. Again, just to show you the plots, this is what it looks like. It's actually very similar in shape to the Gaussian, but it's slightly different parameterized, I guess. So that's what we're going to be doing now. So we specify the correlation equals to the function here is core. Let's see, core ratio is the name of that function for the rational quadratic. The same thing, we say form equals to tilde DAP. We run it. Let's print it to see what is the range estimate of this model. It is estimating the range to be almost 2.7 days. All right, we check the ACF plot. Again, very similar to the previous ones. We check our variogram. Again, we don't see a line being fitted here. And I do want to make this point that if you do have a correlation, your points are, especially if you have more levels, but also you have a strong correlation, you would see a line fit in these variograms. We're not seeing it because we have fewer points that are within the repeated measure, and also because the correlation is not very strong. All right, checking the intervals. So I guess this is the one that I wanted to bring up. So it is different from 0 because it does not include 0 in the range. But notice that this one, the lower is really close to 0, the lower bound of that interval, but the upper is going beyond our data, right? So we only have a range of up to 30 meters, and the upper is going all the way to 120. So this is another way that we can see that this model is not being a good fit, right? It is highly variable, and the upper interval is even beyond our own data range, or I guess maximum distance. All right, let's go on the ANOVA. It has a slightly worse fit than compared to all the other previous spatial correlation structures. So it's not our champion here. Now, lastly, let's do the spherical spatial correlation model. I want to show you the fit again. The spherical is this one here. So to some extent, it's similar to the linear as far as what it tries to fit the data. So let's do that one. We do correlation equals to, this is called core sphere. That's the spherical. And again, we say form equals to tilde DAP. Let's run that. Let's print it. Now our range is being estimated at almost 13 days. Let's check the ACF. Not a lot of improvement, still very similar to the previous models. Let's check the variogram. Still no line there, same reasons as we discussed already. Now the last check we're going to do is, or I guess two more checks. One is the intervals, so we see how precise is this. So it's estimating the lower at 10 days and the upper at 90. So again, going even beyond our data, definitely not a good fit. Okay, so now I want to do a last model comparison on this chunk here, and then we're going to actually select a model, check residuals, and use that model for inference. So if we check all these, especially if we're looking at the AAC column, still our best model is the Mod 3 General that has the lowest AAC. Now, I do want to propose that we use AAC on this exercise. So that's the one that we're going to be selecting. And I want to do some wrangling here to show you some other tricks about this. But I do want to ask you, if we were to use BIC as our metric, which model would we choose? Remember that we want the lowest value here. The default, right? So note, I just want to make a parenthesis here that I think is important. Again, this data, we have very little evidence of correlated residuals, even though we have repeated measures, right? So what repeated measure analysis is going through it and checking, fitting different models and checking to see if any of them are able to provide you an estimate of a correlation that gives you a better model fit. In our case, we tested all of them. And if we use BIC, we would say we tested all of these 9 models and none of them were a better fit or were a best fit when we compare to the defaults. But therefore, our conclusion is that even though we have sampled at different time points that were not randomized or were not randomizable, we still have very little evidence of correlation of the residuals. And therefore, we use the default model afterwards. So, I guess, perhaps, again, this data set in specific do not have a lot of correlation, even though we have repeated measures. But I'm sure that on the ones that you're going to work with, you may, I'm not sure, but I guess you will probably find different results here where a different model may be your best one. And then that's the one that you select. And then after this, we follow our same workflow. So we select the best model, check residuals, run the ANOVA table, decide how we want to extract means, and do a pairwise comparisons and do a plot, right? So after, this is like a parenthesis, I guess, in your analysis of saying, I have to check these things first. And after I check that, then I get back into my normal workflow. Okay, I guess before we do more coding here, any questions about this?
You mentioned that possibly to say that it's worth adding more to the degrees of freedom. So because I think you mentioned last time, if that model is something like different.
Yeah, so well, I will answer, and if it's not what you asked, let me know and I can try again. But so what we're seeing here is that the default model is taking up 40 degrees of freedom, right? And all the other ones are taking at least one more. And that extra degree of freedom is because it is using that to estimate a correlation parameter of some sorts. So if we look here, most of them took up just one extra degree of freedom, right? Because it was just one estimate that it was making from that model. The general actually took 6 extra degrees of freedom because it was the most complex. And so it was the one estimating more parameters. We also had the ARMA 11 taking up 2 because it was the P and the Q estimates, right? So the theta and the phi of that model that it was estimating. So whenever, and this is a great conversation to have because let's say you have a very simple design, you have just like a handful of observations, and then you have repeated measures on top of that. Sometimes if you go through the same exercise, the models may tell you not able to converge, because maybe you have so little data that even consuming just like in the case of the generals, in our case, in the case of the general, consuming 5 extra degrees of freedom from an error may be too much if you start off with an error that doesn't have a lot of degrees of freedom to begin with, which would be the case if you don't have a lot of data, right? So the more data you have, the more correlation you potentially have, and also the more flexibility you're going to have to fit these more complex models. But yeah, so every time that we are estimating something more, we are taking up degrees of freedom that otherwise would be dedicated to the error degrees of freedom. And as we already talked about, the more error degrees of freedom you have, the more power you're going to have to find differences because of that F ratio that we do on that ANOVA. Does that answer your question? Yeah. And also, something else to follow up is consuming degrees of freedom out of the error is not a problem if what you are estimating from consuming that degree of freedom actually helps you with explaining your model variability, right? So just consuming is not bad if that parameter is actually helping your model to be a better fit to your data. In our case here, we can really see that because the best model, if we look at AIC, is actually the one that took out the most degrees of freedom, right? Because it took a lot of degrees of freedom compared to the others, but it was able to explain more, relatively speaking, than the others were, even though they are taking less degrees of freedom. So this is also a trade-off to keep in mind. All right, any other questions? Yeah.
So for if we have to see the variations according to the number of years, then we will also use the same correlations.
Yeah. So then in that case, year would be your repeated measure variable, right? So instead of having factor DAP, you would have factor year and then year on your form. Yeah. And I guess just we're not going to see an example in class of a actual repeated measure in space, but I just want to show you quickly here in one of the models how we would implement that. So let's say if we had a spatial data set where you had, let's say, yield, and then you had a column for X and a column for Y, where X and Y are the coordinates. They don't have to be called X and Y. I'm just using that notation here. What you would do is on your form, you would say X plus Y. And that's how you would specify a spatial data set repeated measure with the spatial correlation structures. That's the only difference. So it's very simple. Okay.
So I have another question.
Yeah.
So in case of any kind of data, do we have to run all these correlations or we just stop after we will get like the lowest possible combination?
I would recommend running all the ones you can run, right? So let's say if you have time series type of repeated measures like we do here, and your intervals are not the same, then you're not going to be able to run all of the serial ones, right? The only one you would be able to run is the continuous autoregressive order one. Or I guess the order doesn't matter, but the continuous autoregressive model. But you can still run all of the spatial, even though if you have temporal data like we're doing here. Yeah, so I would always recommend that you run all of them. I mean, sometimes let's say if you are in a discipline where this is very well established and you know that soil, potassium or phosphorus or something is always best fit with one of these models, you want to make sure you include that model in here, that correlation structure in here. But I think it does not hurt to actually run all of them and get a comparison in the end, because really what we're doing here is trying to find a model that best fit our data, right? And we do that by the more models that we try. So I guess another point that's important here for us to think about is what we can claim, what we could explain in a paper is, yes, I have repeated measures. I did a repeated measure analysis. I checked all these correlation structures, and based on the ones I checked, this is what was the best. So just because, let's say if you were to come here and only test default and compound symmetry, right? Our conclusion would be that default was the best. We're going to go with that. In this case here, maybe that would not be a bad conclusion because as we saw, the default was actually the best one if we use BIC to make our conclusion. But if that was not the case, let's say that you only check these two, but maybe if you check another model, you get a significantly lower AIC, and that would be the clear winner, even on AIC and BIC. Then you have, like, if you only check two models, your conclusion would be one, to go with the defaults, but if you actually ran all of these, your conclusion would change, right? So we do want to be very, I guess, liberal in the sense of trying all the ones that you can, that the model allows to run based on our intervals. And and just select the best. Because also when we run about this here in a paper, we would say we checked all these, and based on the ones that we did check, this was the best. It does not mean that that model is the best, like across all the potential models that exist. It's just within this set of models you tried, that was the best. And so that's why it's important to check a lot of models like we're doing, and also to make it clear on your paper which were the models that you tested. Right, and the ones I'm showing you here are the ones available in LME, so that's why we're using them. You know, I really don't know if there's another package or programming language that would give you even more models. Perhaps there is, but that's why we have to test a lot, say which ones we tested, and then provide this comparison here.
I have a question. Let's say we are in a production field, and the only thing that you have available are environmental information. Within the structure or how we define the model, how would you do that without like a defined design your experiment? Would you still use this?
Yeah, so you're saying, let's say if you have like weather data potentially from a field, right? And you wanna do a repeated measure. So it is an interesting point, because for you to be able to do repeated measure, let me think about it for a second. Because I think that when you establish your random effects here, you do have to have, let me just come to one of the models. So when you establish your random effect here, you do have to have more than one observation within these levels, right? So let's say if you have one weather station in one field, and you get one data point per day, and you're trying to fit repeated measure, I never tried doing that. So I guess my answer is I don't know what would happen. But my intuition tells me that if you don't have repetition within the level that you have repeated measure, I don't know if that would work. Yeah, but I'm not sure. Yeah, that's a good question, and I'm sure that like, but then one thing that you can think about, at least in this, with what we're doing here, is we want to compare the means of different dates and the potential interaction of that with treatments. So that is our main goal here, right? Is compare means. And so if with that mindset, I guess you would not be able to compare mean of temperature from day to day, for example. Perhaps you could do windows of like 5 days and get 5-day points within those windows, and then have that window as a repeated measure if you want to compare means, because that would give you a mean estimate of the window and then the repeated measure within it, right? But so these types of models, they are used also for, so if you're trying to predict time series, and so this is not a time series analysis itself because we're doing analysis of variance. A time series would be more like on a regression approach, where our variables here would not be factors. So would not have clear radian days as factors. They would actually be like numerical variables, right? Where both your y and x sides are numerical continuous variables. In that sense, I have not done that myself, so I would have to do some digging to understand how we would implement that. But people do that with repeated measures to get a better prediction, especially, right? A time series prediction into the future of what would happen based on what has been seen. So it's, yeah, maybe there are ways, even if you don't have replication within the level of repeated measure, like having a weather station from one side only, or one weather station only. But yeah, I guess I'm not sure exactly how that would be implemented.
Let's say in the case you were saying comparing two continuous measurements for the response and the explanatory variables, would you just put let's say the most sensing data you are calculating as a reflection system as your explanatory variable, then you would just omit the random component?
So you would still have to have a random component, because that sets the level of the repeated measure as well on the correlation. Yeah, so we normally don't do. I mean, I don't think I've done myself an analysis of, like, let's say I have a repeated measure of remote sensing, and then I use this mostly because we're using different dates almost independently. Like, I don't really have an interest of, I haven't had at least an interest of knowing how things are changing from date to the next date. Is more what's happening within the dates. So I have not had to run this on a regression type of approach. But if you do that, and if it is experimental data, you would have those replications within the date, within the repeated measure variable. So you should still be able to do it. And I think that would be an easier, like, as long as you have replication, that I know that would work, the model would fit. I haven't tried fitting a model where you do not have replication at the level of the repeated measure. So I don't know if the model would fit that way. But it's something, you can try. And there's definitely, the code here overall for repeated measure we have, so you can just adapt it and see how it goes. That resource, the Pineda and Bates book, is really good. They have some really good examples, and even I think they have some regression examples as well in there that you can use as a reference. Awesome. Any other questions? All right, so what I want us to do now is, here on the final model comparison, I do want to do a little bit more wrangling here just to show you, like, how we can perhaps automate this model selection a little bit. I guess not the model selection, but just the decision of which model was the best, how we can do that. So this ANOVA, so when we print this ANOVA here, this is not a data, let's see. Well, it is a data frame. So it is already a data frame. But if I want to have, so if you look right here, I think this concept, I just saw somebody had a question in the chat. Let me go back for that. So Kriti was asking, for time series data, if we have 12, 18 data points for a day, should we run all the raw data in the model or the mean of a specific day and fit them on a model? So, okay, so what Kriti is saying is, so let's say if you have weather stations that measure, at a larger frequency than just a day. If it is observational data, I think you have more flexibility with how you would treat this, Kriti. Again, I guess it's somewhat related to what Jonathan was asking as well. So if you have many points within the day, and then you have also many days, I guess first it depends on what would be your inference scale, right? So are you trying to predict or explain at the hourly time scale or at the daily? I think from your question, it seems like you at the daily scale. So in that case, if you're doing at the daily scale, I guess you could use those points perhaps to show you, if you still have the hourly data, but you want to model at the daily level, you could use those points kind of as we were talking about creating windows of intervals, that your day could be that window of interval when you have hourly data within it. So I guess you could include it in there. You just want to make sure that you set up your area structure correctly, so you don't have, because really, if you think about it, if you have hourly data, but your interest is at the daily level, then the hourly is almost a subsampling, right? You're subsampling within the date instead of getting at 1 point for the date. So if you want to properly model that, you just have to make sure that your error structure incorporates that, and you do that with nesting. So it would be a similar concept of what we've been doing with the split plots. Let me get back to a model here, so let's say you would have your random effects. I mean, I'm not sure about the whole situation. So just a very, very hypothetical example here. You would have your random effect being days, and then having hour, or whatever that column is for the hour, nested in days, but then you're modeling here days. So you're making clear that that's how we would specify that your hourly data is like subsampling within the date. So you can still have the column. You don't have to calculate the mean of the day if you don't want to, even though on the error, so maybe another way to think about this is if you do have subsampling on your study. So let's say that you go at harvest and you sample 4 places in your plot, but the plot, so the way that we determine subsampling is to know what is your experimental unit. And that is determined by how you apply the treatments. If you apply the treatment to the whole plot, that is your experimental unit. And if you go and take multiple samples of the same date within the plot, that is subsampling. Now, in that case, if you do have subsampling, you should make sure that your model incorporates that information on the random effect. Because if you don't, then you're going to come to a model that has 3 times the number of degrees of freedom, because now instead of taking 1 value, it's taking 3 for each plot, which is not correct, because those 3 are not independent. I'm sorry, they are dependent. So I guess in this case, critique could be a similar conversation as far as your hourly data points being like subsampling within the day, that you have to set that up correctly here. Otherwise, you're going to have too many degrees of freedom that would not represent the true error of what you're collecting. And again, comes back to the fact that if you do have subsampling and you do not properly specify the model, your degrees of freedom of the error are going to be inflated, which is going to give you smaller errors. It's going to give you more power to find statistical differences, but erroneously. You should not do that if you have subsampling. Awesome. I think, I'm sure this was very confusing because I'm not showing you any visuals of what I'm talking about. But yeah, we can chat later individually as well if you all wish to kind of narrow down more on your cases. All right, any other questions? All right, so let's go back here to our final model comparison and selection chunk, where we have that ANOVA function lowercase a with all the models that we tried. So what I want to do here, and I guess I want to ask because now we're going to decrease the complexity of the topic, I guess, because there's just going to be some data wrangling. So I want to tell you what I want to do. I will help you a little bit, and then I'll ask for your help after that. So for me to not rely on my eyes here and just looking at these values and making a decision, I do want to create a code that allows us to sort these columns accordingly. I do want to show some steps that maybe would not be necessarily needed in this case, but I think it raises the opportunity for me to show you some more tricks. So here in this, it is a data frame as we're seeing, but something that I don't think we've seen yet in this class is that the model names are actually, I don't know if you can fully grasp this, but they're not a column. They're actually the row names, which is something that sometimes you come across in R. It's not the most common way of having things. I believe Python uses this more frequently than R. But right now, this is not a column. These are the row names. And let's say I could basically not have this as a column if I didn't want to. But I think it's useful to have this as a column because then we can manipulate it if we need to. So I want to show a function that we have not seen yet, which if you come back to this ANOVA here, let's give it a pipe. And there's a function from dplyr that's called row names to column. So this is going to remove those row names and move them into a column that inside of this function here, if you say var equals 2, you can give the name of that column. I want to give this name as model name. So if you use this function here, it's actually going to do more than only that. It gives us this, and this is, I guess, let me just make a parentheses. So right here, we use row names to column. What I would normally expect is just to see a column called model name with those model names, which I don't know if it even did that for us. Yeah, I don't think it did. So let's do something else here. So before we ask row names to column, let me force this ANOVA output to be a data frame, even though it seems like it is a data frame, but when we're doing this, it's not behaving like I would expect. So let's just force it to be a data frame. We can use the function as data frame to do that. So if we just run that before connecting with a pipe with row names, yeah, I think this is a better way of dealing with this. So we did as data frame. It looks a little bit different now, but we still have these values as the row names. They're not a column, but we still have all the other. We have this call new function that is just telling us what was the formula that was used for each one of the models. Maybe that would be of interest for you. For right now, it's not of interest to me, at least. Then all the other columns we already had on that output of the ANOVA. So now that we have as data frame, if you connect that with the row names to column, it's going to bring in those model names as under this column here called model name. So this is an actual column now. It's not the row names anymore. It's a true column. And this, it happens if I think sometimes I'm doing like I'm taking the output of the ANOVA tables we used previously, where you have sources of variation, degrees of freedom, p-value, and so on. Sometimes I want to make those into tables, and I use the as data frame, and then the effects. So let's say potassium rate, N rate, and so on are row names. That's another case that I've come across that I want to take row names and force them to be a column, which is what we're doing here with this function. All right, so I do want to simplify these names here and just have them all. So we see like we have a dash, we have a dot, so we have different ways of naming these columns or different patterns. I do want to simplify that to all lowercase. We've done this maybe a few times in this course. Can anyone remember what function we used? Clean names, right?
Clean names from janitor, yeah.
Yes. So we did not load janitor. So if we just want to use this function, we can just call the package name and then colon, and then clean names. So that's a way that we can also use a function without loading the package. So now our columns are all lowercase, easier to refer to them. I do want to select just a few columns here because we have some that we're not using them really. So let's add a pipe. I want to use a dplyr select. And I really just want to keep model name. So that's the one that we brought in from the row names. So model name, model, which has like a model number. This column here was coming from the ANOVA function already. DF, so we keep an eye on the degrees of freedom, and then AIC and BIC. So I'm leaving behind all the others and just keeping those to keep things tidier. All right, so now we can more easily, and I guess more informatively as well, arrange the columns either based on AIC or BIC and use that to have our best model on top, and that would be the one we select. So if we want to sort this by AIC, what column do we use? Or sorry, what function do we use? Arrange, right? So we use arrange. And first off, let's arrange by AIC. So that the default is going from lowest to highest. So we see here that if we use AIC, mod 3 gen is the best, as we already knew, but we're just confirming that here. So we don't just trust our eyes and actually have a way to confirm that. Now, what if we actually arranged by BIC? What would happen? So we can just follow that up with an arrange BIC. If we were choosing BIC, we would choose the default model, as we already saw. And again, this is because this specific data set, even though it was repeated measure, it was not very strongly correlated across those repeated measures, across those dates. So that's why the mod 1 default, it is such a strong contender of this list. If you have a certain correlation, the default one is going to be way down this list and most likely not be the one you select. Okay. Yeah, I think what I said is just what I have in these comments here. So what I want to do next is just assuming that, so if we decide to use AIC as our metric, and then because of that, we assume the best model was the general model, so Mod 3 Gen. The next thing we're going to do here is, so we basically did the repeated measure analysis here, right? Now it comes back to our normal workflow of checking residuals, checking the ANOVA table, deciding how we want to extract means, and so on. I think this is a good stopping point for us to take 5-minute break because we're going to 11:30 today. So let's take a 5-minute break and then we'll come back and continue that exercise.
Dr. Bostos, I think you are muted.
Yeah, sorry, those online. I was having a conversation with a student here in class about his design. So, all right. So let's get back to our exercise and continue running here. So after looking at this and using AIC as our metric of choice to select the model, we would make the decision. I guess we have to run again and stop in the pipe there. We would have the decision of selecting Mod 3 Gen as our best fit model. Right, so with that in mind, so selecting that model as our model to then use for inference, the first thing we would do here is calculate the residuals. So we're going to check residuals. One very quick difference you're going to see in this code. So I'm using the augment function to get the residuals of the model. And then as before, so before we were calculating the studentized residual, so the function here was rstud, I think. Maybe the arguments were a little bit different as well. I tried using that function here and it did not give us the residuals. It was not able to calculate. So I changed from using the studentized to using the standardized residuals, which it has a different formula behind the scenes, but it is giving us one type of normalized residuals anyways, which is the goal here, is to use a normalized residual so we can look for outliers. So that's why instead of calling this stud resid as we were before, I'm calling STD for standardized. The function is different, and I think the arguments are a little bit different as well. But we're still getting a normalized type of residual that we can use to check the outlier assumption. So if you first load the BrewMix package and you create this object, this is the same. So if you remember what the augment function does is it takes your data set and it just appends other columns with the residual information. Every observation on your data set has a residual because it's going to be the difference between what the model is predicting that is and what the observation actually is. That's the residual, right? And then also creating that column, the standardized residual at the end as well. I think I left you here all the code, and I just want to explain one difference that I made here. So on previous exercises, we were calculating. So here, sorry, I'm kind of getting ahead of myself. So the assumptions here, remember that for linear models, every time you have a variance component in the model, you have to check assumptions for that variance component. If we go back all the way to the CRD example, which only had fixed effects in the model, every model, even fixed effect models, have at least one variance component, which is the variance of the residuals. Every model has a residual term. Every residual term has a variance component associated with it that requires to check assumptions. So if you remember that, saying that the residuals, let's say EIJK, are IIDN, identically independently distributed normal with a mean of 0 and a variance of some sort. That is the sentence that, because of that sentence, we check assumptions. That is where our assumptions basically are summarized in that sentence. And then every time you add a new variance component to a model, we have the same assumptions. So check that they are IIDN with a mean of 0 and a variance related to that level, right? So right here, because this is a split plot RCBD, if you remember, we used this runf function before. So if I just run this by itself on the model object, we get here the random effects of the block, of the potassium rate inside a block, of the nitrogen rate inside potassium rate inside block. In this case here, we did not have this level before. Here we have, because we have repeated measures and the days after planting are the lowest level of the hierarchy, which makes us need to bring the nitrogen rate nested in everything else as part of the random. So it does not end in the error, just days after the planting and in the error. So we have these 3 levels of random effects that we have to check assumptions as well. That's what we're doing here. So what I'm doing here is calling this runf function, and I'm using this notation here to sample the first component of that list. Because if you just run runf, again, is that output that we were seeing below, it has this first component, the second component, and the third. So the first one is just for the block. So if I run this now with that brackets one notation, it's just going to return to me the one for the block, the first component of the list. And then I'm feeding this right into a ggplot. So I'm not assigning this to an object like we were doing before. I'm just feeding that right into a ggplot for us to look at the distribution with the QQ plot, the quantile plot. So this is the output that we get. Again, we only have 4 blocks, so it's not a lot of data points. I mean, they don't look bad, I guess, as much as we can tell. We don't have a huge distance from those tail points to the line, but we only have 4 points, so it's harder for the algorithm to really give us a good estimate of what this distribution should be anyways. Now doing the same thing, but for the second level of that hierarchy, so the random effect associated with potassium rate nested in block, which I'm getting here because I'm changing the number on the brackets to 2. So if you just run this up until the bracket, to see what that gives you is the random effect of potassium rate within block, and we have 12 observations because we have a total of 4 blocks and 3 potassium observations, or potassium levels, sorry. So if we run this to check that assumption, it doesn't look bad either. Some deviation on the first and last one, but nothing too worrisome. Now, the next one to check is the last random effect component, which is nitrogen inside potassium inside block. I get that by using the 3 on the brackets here. And if we run that, this is what we get. So again, some slight deviation in the tails, but nothing that would worry me really. So we check the assumptions basically for the random effects part of the model. Now we're going to check the assumptions of the residual of the model. So the EI, JK, and perhaps more indexing letters than just that, but the error of the model. So this is just the residual that we calculate on top with the augment function, right? And we've seen this before. So this, we can actually calculate the fitted by standardized residual. I'm adding the smooth line. And just something to bring to your attention again. In this case here, so if we just compare mod3 gen, which is our split plot, so our randomized complete block design with blocks random split plots. So there's a difference in the data now between this and the previous one, which is the fact that now we have another variable that has 4 levels, that is the harvest times, right? So just because of that right there, we're changing the data. And even if we were to fit this whole data to the same models as before, not considering sampling date, harvest time, sorry, our residuals would already look different because the data is changing, right? So remember, residuals is the difference between your data and what the model thinks data should be. So if you change data, you change residuals. In this case, we're changing the data, but we're also making the model more complex by doing the repeated measure correlation structure, in this case, general. So we're changing the data and the model. And that's why these residuals look so much different than the previous one when we just had randomized complete block design with blocks random and split plots. So these residuals look very different from before. If you remember before, we kind of had this pattern, even though it was still covering the 0, the error bars were covering 0, but we had this very strong or stronger pattern than what we see here. So here we're not seeing that pattern because again, we're changing both the data and the model. So residuals look different. Really nothing too worrisome here either. It doesn't seem like we have a pattern in the residuals. Nothing is beyond 3 or -3, so no outliers. It does not seem like the variance is increasing as we increase the x-axis. So homogeneous variance, normal residuals. Well, I guess normality we're not checking here necessarily, but independence, it seems like it's checked. No outliers, and variance homogeneous. So nothing to worry here. And then to check the normality is when we use the QQ plot on the residuals. Again, a little bit of a deviation on the upper tail, but nothing too drastic. I wouldn't really worry much about it. So overall, check the assumptions of the mod3 gen model. Looks good. So let's now check the ANOVA table. All right. So I think I don't remember now what was the ANOVA for the default model. Let's see if I do that. Well, I guess for now, let's not think about that. I think that comes later in this script. But just looking at this ANOVA table, which again is based on the mod3 gen model that had the general correlation structure, I guess I'll focus here since we have the p-values in the terms. How would you extract, like what line on this ANOVA table would you use to extract means into pairwise comparisons based on the p-values you were seeing? The three interaction, right? So the most complex interaction here is significance. So significance between days after planting, nitrogen rate, and potassium rate. This is what we should look into. And again, you may decide to show the other means in comparisons if you want for the main effect of days after planting and the two-way interaction of potassium and nitrogen rate. However, you should really not discuss much or make a lot of inference on them because you have the significant interaction, right? So if you were to show just one thing here, I would show the breakdown of this interaction and leave it at that. All right, so I left you the code already here so everything that started at the residuals is the same as we've done before, right? So all the complexity of the repeated measures has already happened when we tried all the models and selected a model. Once we select the model, everything falls the same. So I'm leaving you most of the code here since you're already familiar with it. I do want to make one parenthesis here, which is not specific to this analysis, but every time your error terms begin to get complex, to become more complicated, in this case here, it's a somewhat complicated error structure because we have, so if you think about it, we have nitrogen rate nested in potassium rate nested in blocks as a random effect. And then on top of that, we're also modeling the residual with a different correlation structure. So we have a good amount of complexity in our error specification of this model. So if originally I wanted to show you for us to have the colon here, so don't have any structure, just get all the means for all days, all potassium and nitrogen rates on the same level and compare them. I did this, and at least on my computer, I think I was waiting for over 10 minutes and still did not have a result. So I decided to abort that and not show that in class because it would be a waste of our time to do that. So what I decided to do instead is to compare different days after planting within nitrogenate and potassium rates. That's why I'm doing here. If you remember, we did have a conversation that every time you have at least a two-way interaction that you're getting means and doing pairwise comparisons, the way that you specify those terms here, either using the colon or the vertical bar, will impact how your means are compared, right? In this case here, you're going to see when we do the plots, we're going to talk again about how we can interpret this specific way of getting our means. If I just run this part of the code so you see the structure that's coming from it, this is what the mean structure is being set up. So I'm comparing all combinations of potassium and nitrogen rates within a date. Or, no, I'm sorry. It's actually the opposite. I'm sorry if I confused you. Because I confused myself. So I'm actually getting inside of one combination of potassium nitrogen rates and comparing the dates within it. So here we're answering the question of, is a given treatment increasing over time significantly? Is that increase significant, right? This is the answer that we are finding with this specific way of breaking down the means, which would be a different answer if we did K rate and nitrogen rate vertical bar FDEP, right? So let me just do that so you can see how that would be different. So if we did this and we stopped here to look at the structure coming from EMEs, now I'm going inside one day after planting and comparing all the potassium nitrogen treatments within it. I hope you can grasp that these are different, and the way that these are going to have an impact is on the letters, right? So the way the letters are calculated, are estimated, and what they mean is going to be different depending on which type we use. All right, I just want to go back to having FDAP, vertical bar, potassium and nitrogen. I'm feeding that right into a CLD, and then doing the wrangling that we do to get this as a data frame, get the letters without the white spaces, and then creating treatment name. I'm doing also this in previous exercises was probably 3 or 4 different chunks. I'm just piping them all together to simplify things. And if you're doing this on your side as well, you can do this. In class, especially the first times we see something, I like to break it down into parts so it's easier to understand. But here we're just combining maybe 3 or 4 chunks into one. All right, so if we run that, we get the data set with all the factors. So days after planting, potassium, nitrogen, the EME, and the letters, and the treatment name. And then I left you all the code for the plots. I'm not going to walk through what each part of it is doing, other than tell you that I want to show the box plots with the raw data and also the letter separation. So bringing the raw data and the statistical summary on the same plots. So if we run that, this is what you would get. I guess it's not very, very big here. Let me see if I can. Maybe that helps a little bit more. So what we see here is each panel of the facet is one combination of that nitrogen by potassium. And then on the x-axis, we have the harvest time in days after planting. And we have yield on the y-axis. And then we have the letters, right? So what we are comparing here is basically how a given treatment is increasing the yield as we increase the harvest time. They're all, so within a treatment, I think all of them are here A, B, C, D. If we just take a quick look. Yeah, I think they're all A, B, C, D overall. And just to remind you, because of the way that I extract the means and how that impacts how the pairwise comparisons are done, the only comparison I can do is within this plot, right? So the A here does not mean that it's the same as this A. I cannot compare across treatments. It's just within the treatment over time. If that is your hypothesis, this is how we would extract means. This is one of the ways you could show this data. But if your goal is to show maybe the other way around as we were doing as far as taking one date and comparing all treatments inside of it, you have to change your EMEs. You should also change the way you show your data, because that is going to lead the intuition of your audience on how they would interpret it. Okay, so now I just want to assume that if we had used BAC and we had instead chosen the default model to be our model that we would do inference, right? So we're just going to go through that here and do a few comparisons. I'm not going to go through the residual check again, just for time's sake, and because we already did that for one of the models, so you know how we would do it. So we're going to skip the residual assumption checking here, but just get right into the ANOVA table. So notice now again, I'm bringing here the mod 1 default, which is the one that we would have used if we use BAC as the metric in this case. So what I want to ask you, and maybe you can very quickly work with your neighbor, is take a moment to compare this ANOVA and the one from the general model that we just ran above, and tell me if you see any differences there. We can take just a couple minutes here just to quickly do it. So one of you can stay here on the ANOVA, the mod 1. The other one can go to the ANOVA, the mod 3 that we did you know, a few chunks above. So use your outline to get there, and just think for a moment what you see there, if you see differences. All right, I see some great conversations going on, but I just want us to keep moving so we finish this exercise today. Anyone wants to share what they observed?
Again, Dr. Bastos.
Give it just 1 second, Austin. Sorry. Let's go. Yeah, so it is just saying the three-way interaction was highly significant on the general model and not so strongly significant on the default model, right? That's definitely something that happened there. Austin, did you want to say something?
Yeah, I was thinking very similar to Anish, and just that the big it seemed very similar in certain spots, but with the F days after planting, there's a difference there, and then with the K rate of kilograms per hectare and nitrogen rate kilograms per hectare with the F day per planting, the last row there, it did there was an other more difference, and other than that, it did seem kind of similar in other categories.
Yeah, I agree. Anyone else has noticed something different from this that you'd like to share? All right. Yeah, I mean, that was really the main difference that at least we could observe here. One thing to notice is, or to just keep in mind, is this degrees of freedom column here is for the degrees of freedom of the numerator. And the degrees of freedom that get impacted by estimating more parameters are those of the denominator of the F ratio, which are not these, right? So that's where we would see a change depending on the model and having different parameters being estimated, different degrees of freedom of the error. All right, so let me ask you all something. You don't have to pair, but we can just talk about something very quickly here. So if we had decided to go with the default model, like we're seeing here, this ANOVA table, and we're using a alpha value of 0.05, what would you do to get means and do pairwise comparisons? Which terms would you do that for? Yep, so we would definitely extract here. So I guess we would not extract the last one because that's above our threshold of 0.05. So we would not do this one as we did before. We would do this one, and is that all? Okay, so here's a good point for us to talk about. So notice that our most complex interaction here, in this case, with alpha 0.05 was K rate and nitrogen rate. And then we have the main effect of days after planting. What I would do is actually do two plots, one for K rate and nitrogen rate by itself, and then maybe a plot or a table or even just on a sentence since we only have 4 dates. But I would explicitly bring this main effect by itself, right? So what we want to do is look at the most complex one and see what's in it and break it down. But everything that is not part of it that was also significant, then we keep looking up, right? So in this case here, I would show the one plot with this interaction here broken, and then another one for the days after planting by itself. Now, in our case, the main effect of potassium and nitrogen were not significant, right? So we would not show them anyways. But let's hypothesize that the 2A interaction is significant here, and then all 3 main effects are also significant. I would show the breakdown of the 2A. I would show the breakdown of days after planting. I would not show the main effect of nitrogen and potassium because they are already part of a more complex interaction term. That's the one that we want to show. Any questions about this? All right, so here, basically just doing the EM means again with days after planting within different levels of nitrogen and potassium, just like before. I'm calling this wrong, even though it's, it's not wrong I guess wrong if we're using AIC as the metric, but it would be the correct one if we're using BAC. So just got those means there, and then just getting this plot here at the end. So if you were to run this on your side and also take a closer look at the letters, I'm just going to save you all time. They're the same in this case. This is most likely because we had, even though mod 3 gen had a lower AIC than default, but they were still very close. And overall, we did not have a very strong evidence that there were correlated errors, even though we use a time series, or even though we had a variable that was not randomizable, which was the time of harvest. So because of that, these letters were not different. But again, if you run this on a data set that has time or space as part of it, as part of the fixed effects, which again, you can not randomize time and space, and you run this analysis, and then you find that one of the other models other than the default is the better fit, and you go through the exercise of comparing their outputs, they will most likely be different. And repeated measures, just to bring this point again, repeated measures does not impact the means. The means would be the same. Repeated measures is going to impact the error, right? So the error is important because the having a model with the proper error structure will change your p-values of the ANOVA. It will change your mean, the error of your means, and it will change the letter separation when you compare one mean with the another one. So getting the right error of the model is very important to make sure that you're finding the correct error structure that represents your data, and then you can make inference properly on those differences. Okay, let me see if there's something I miss here. Okay, I guess, just to make again this point. In our case here, our data was not very strongly correlated with when it came down to the errors because of that time series variable or that the harvest time variable. But that does not mean this would happen with every data set. Most likely it will not, especially as you have more levels of that repeated measure variable. So if we had 10 sampling points, perhaps that we would have seen a stronger correlation. Or maybe, if you have a spatial data, that's even easier to get multiple levels of that. So just keep that in mind. Just because we did not find much evidence here, it does not mean that that would be the case with your own data. So that's all that I had as far as this exercise. We finish it up. When we come back from spring break, we're gonna start talking a little bit more starting to shift between experimental design analysis and start going more towards machine learning. We're gonna start very slow in the sense of we're gonna check or I guess review some concepts of linear regression, make some comparisons there, we'll just learn about some models to use linear regression or no, not only linear, but use regression models to find optimum points, which we do a lot of times in ag-related studies. And then we're going to start getting more into the machine learning. We're going to be pulling data from some open source databases, start creating features out of the features that we get, and then start using those features that we get to then train machine learning models of different types. Okay, before we wrap up, I want to tell you that I sent you all the survey this morning. Please, if you can, please respond to it by today, because then I can assign you groups. And what I'm going to do then is assign the groups and give you instructions, clear instructions of what I want you to do. You're all going to have different data sets. So I want to be flexible in some parts, which is going to be related to the data sets you're going to use. At the same time, we're going to have some structure that you all should follow. So for example, we're going to work in pairs. You're going to work through GitHub. So I do want the person that has data set to do all this setup here, upload the data, and then invite the person that does not have the data set to collaborate on that project, on that GitHub repo, and then you can work off of GitHub together. I'm going to have some more thoughts about that. One thing that happens when we work together with people in GitHub is that it may have merge conflicts. We did not go through how to fix a merge conflicts, but I guess what I would recommend is perhaps you work together, but in different scripts. So maybe you would say, well, you can do the data wrangling part. So a person that does data wrangling has a script for that they import raw data, wrangle, export the wrangle version. The next person maybe run the model or something like that, just so you avoid merge conflicts. I guess at this point, that's probably going to be better. If you're actually working with other people in real life, you're going to have merge conflicts. And maybe depending on how much of that becomes a problem for this exercise, we may have a period of class just to talk about it, how to solve them. It's not very difficult, but it's just something that can happen. And I don't want that to distract you from the actual project. That's the goal. Yeah, so, and also remember that even though, so both the person that has data set and the person that does not have the data set, I will grade you based on how much each one of you worked, and I will be able to tell that because I'm going to check your commits. I'm going to see who is doing what, when, how much. So make sure you try to more evenly split your workload, so both people can work and help each other. And really rely on each other, because just because it's your own data set, it does not mean that you have all the answers. Like maybe someone else has a different perspective, has a different experience, has a different thought of how you should show a given plot or do something, or, I guess try to rely on each other and learn from each other as well, and not just, people working the same project, but not talking to each other much and running ideas by each other. All right, so I think that's it. I will send you instructions on paper or on a QMD actually by tomorrow. And then we can follow up. If you have any questions about that, please make sure to post on our 2024 GSA issues first. Even if it's just like a general question about the project, post there, because maybe somebody else is not going to know the answer because that would come from me, but at least I can answer in a place that everyone can see what the answer was. So I don't have to repeat myself by email to each person that has the same question. So if you have issues or questions, use GitHub for that, for us to talk about it. And I guess that's all from my side. Anyone has any questions before I take attendance?
I have one quick question, Dr. Bastos.
Yes.
You know, I don't know if you know, like maybe it's the even ratio of people that have data versus don't have data. So my question is, if we do have data, is there enough people that, like splitting into groups that if we do have data, we're for sure going to use our data, or if we have too many people have data, or some people just not going to get to use their data?
So I think what we can do is, like if a lot of you have data and, you know, I want you to work with your own data, then maybe you don't work in groups, but still use GitHub. Remember that on Git and GitHub, your current self is working with your past self and your future self. So then use yourself in different time points as your partner, I guess. But yeah, so I think from a show of hands last time, I think we have probably a good even distribution of people with and without data. But if we have like a lot of people have their own data and you want to work with it, you don't want to, you don't want to spend this time working on someone else's data. If you have yours, then it's completely fine to work alone. So I'll make that call when I see the answers from the survey. All right, so make sure to claim your attendance if you were in class, and I'll see you after the break. So have a good break, enjoy it, and yeah, let me know if you have any questions in the meantime, and we'll go from there. Thanks, everyone.